This one says, draw a picture and write the chemical formula that occurs when a lithium atom and a fluorine atom react. So one of the reasons we drew all the particles in these atoms is we want to see how and why they're going to interact with each other. So we want to take a lithium atom and a fluorine atom Lithium has one valence electron. That is one electron in its outer shell. Fluorine has 7 valence electrons in its outer shell. Lithium would like to have a complete outer shell. Fluorine would also like to have a complete outer shell. And so fluorine actually has what you could call a space here, or a hole. It would like to fill that hole, is the idea. So we can see here how lithium's outer valence electron could be used to fill the need that fluorine currently has. This type of bond is going to be called an ionic bond. That's a bond between a metal and a nonmetal. So elements on the left of the periodic table are generally metals, and elements on the right here are nonmetals. But what we find is that metals, they are electron donors. And nonmetals are going to be often electron receivers in an ionic bond. So when lithium gives its electron to fluorine, we're going to write that chemically as a compound. And we'll just simply write it by sandwiching Li and F together. And this is called a compound. We can give it a name. Lithium fluoride. So even though the element is fluorine, we'll use the suffix IDE whenever you have an ionic bond taking place. You just replace the INE with IDE, and then that is going to be its name, lithium fluoride. Lithium wants to let fluorine borrow its electron, in a sense, and fluorine is happy to accept lithium's electron. And so the electron will hang out by fluorine. So we can actually remove it from here and just put it here. But now they've created a bond. So lithium forms now an ion. That's why it's called ionic bonding, because now lithium only has 2 electrons and 3 protons. So it forms a positive ion. And fluorine now has more electrons than protons. It originally had 9 protons and 9 electrons, but now it's got 10 electrons. And so the fluorine will form a negative ion. You can try it for yourself here with sodium and oxygen. Now we want to draw a picture and write the chemical formula that will occur if sodium and oxygen react chemically. All right, so for sodium, we see in the periodic table that it is in row 3, and it's got 11 protons. So there's its nucleus. It's going to have a full first shell and a full second shell. And for the third shell, we're going to have just one electron. Sodium is a highly reactive element because it'll easily give up that one electron. That's sodium. Now we also want to draw oxygen. Oxygen has just 8 protons. It's got a full inner shell, but it does not have a full outer shell. It's only got 6 electrons in the outer shell. So sodium wants to give up an electron. But the thing about oxygen is, if it could have 2 electrons, then it could have a complete outer shell. It wants to have 8 in the outer shell, but right now it's only got 6. So even though one atom of sodium could help solve the problem for oxygen, one atom alone is not enough to complete the puzzle here. And so what we want to do actually is bring in another sodium atom. And so one thing we can do when we have a sample of sodium that's going to react with a sample of oxygen is we can bring in more sodium atoms as needed. And so we'll bring in another sodium. And you can see what's going to happen here is, so one of the sodium atoms gives its electron to oxygen, and the other sodium atom gives its electron to oxygen too. This completes the puzzle, but it shows that it requires 2 sodium atoms in order to satisfy an oxygen. Now when we write the chemical formula for this, we're not going to just write NaO this time. We want to show that it's required that we have 2 sodium atoms to complete the puzzle. And so to do that, we'll use a little subscript on the sodium, Na2O. Na2O means that it requires 2 sodium atoms to satisfy 1 oxygen. And this will be the chemical formula of the compound that's created when sodium reacts with oxygen. The next example says, what will happen when beryllium and chlorine react? Beryllium is in the second column of the periodic table. All elements in this column want to donate 2 electrons. What ends up happening is all elements in the first column want to donate 1 electron. They all have 1 electron in their outer shell. But all elements in the second column, they want to donate 2 electrons. Chlorine, on the other hand, is found over here in column number 17, and that's also called group number 17. It is the second to last column of the periodic table. Now we know the last column here, they all have a full outer shell. They're called inert, meaning they don't want to react with anything. But the second to last column, they actually are highly reactive. Only 1 electron is required so that they can have that complete outer shell. So beryllium will donate 2, and chlorine will accept 1. Beryllium has 4 protons in its nucleus. It has a complete first shell and 2 electrons to donate in its outer shell. That is beryllium. chlorine has 17 protons. It's going to have a full inner shell. It'll have a full second shell. And for its third shell, it's going to have 7 electrons. Now, since chlorine has 7 in the outer shell, it wishes it could just get one more to have that complete outer shell. Problem is, though, beryllium wants to donate 2. And it's not happy just donating 1. It needs to get rid of that second one, too, in order to react fully. So how can we solve this problem? So here the puzzle is not complete. The formula between these two cannot be just BeCl. We need to have everybody satisfied here. So a way we can do that is to bring in another chlorine. So if we bring in another chlorine atom, we see that the puzzle can be complete. Beryllium could give one of its electrons to one of the chlorine atoms and give the other electron to the other chlorine atom, and now everybody would be happy. Beryllium would have gotten rid of its 2 electrons, and these 2 chlorines would be happy too because they would both have 8 electrons in the outer shell. So the formula is actually not BeCl, it is BeCl2. So the subscript of 2 tells us that 2 chlorine atoms are required to satisfy 1 beryllium atom, and this can be the chemical formula. It would be, in words, beryllium chloride. For the next one, we want to do an ionic bond between the metal aluminum and the nonmetal oxygen. So, if we go to the periodic table and zoom in on the entry for aluminum, we can see that it has a +3 in the upper right. Now that's called an oxidation state. It is the type of ion that aluminum tends to form when it reacts with a nonmetal here. So what this means is that aluminum tends to lose 3 electrons. Oxygen has an oxidation state of -2, and so what that means is that oxygen tends to gain 2 electrons. That should make sense because oxygen is in the second to last column. The last column would have a full shell. This column would want 1 electron, and oxygen needs just 2 electrons to have a full shell. We can use those numbers to figure out what the arrangement must be of aluminum and oxygen atoms. So, aluminum, if I was to draw just the valence electrons for it, it has 3 electrons in the outer shell. Alright, how do I know that? I know that because we would start with sodium having 1 electron in its outer shell. Magnesium would have 2. And then when you jump across the gap, aluminum has 3 electrons in its outer shell. So I can draw those valence electrons like this. It's called a Lewis dot structure. Now we could also draw an oxygen. Of course, the oxygen has a complete inner shell, but it does not have a complete outer shell. Oxygen wants to accept 2 electrons. Now this puzzle is not complete because even though we could send one of the aluminum's electrons here and the other electron there, we don't have anywhere for that third electron to go. And that means that the reaction could not take place like this. So we have to figure out the right combination of aluminum and oxygen atoms so that perhaps the puzzle can be made complete. So let's say, just hypothetically, that we bring in another oxygen atom to give that last electron somewhere to go. All oxygen atoms accept 2 electrons, but here we see we've only got 1 to give. So the puzzle is yet again still not complete. We need another electron to go here, so we may wish to bring in another aluminum atom. But all aluminum atoms come with 3 valence electrons. As you can see here, one of those electrons could be used to fill that gap there, but we still have 2 remaining valence electrons that have to be gotten rid of somehow. So I believe that if we were to bring in one more oxygen atom, then the puzzle could be made complete. There's 2 electrons left to give. Oxygen accepts 2. So now everybody is satisfied. But it required 2 aluminum atoms and 3 oxygen atoms. Now, is there a shortcut for this kind of process? There is. It comes from the oxidation states that each of these has. So aluminum forms a 3+ ion, and oxygen forms a 2- ion. So the shortcut is you can actually just cross the numbers here and let those oxidation states become the subscripts, but they have to be switched so that aluminum takes on the 2 and oxygen takes on the 3, and that is a shortcut for finding the right combination of the metal and the nonmetal. The name of this compound would be called aluminum oxide. And it is Al2O3. Next problem says, write a chemical formula for iron, parentheses 2, chloride. And I see after that, we're looking for a chemical formula for iron, parentheses 3, chloride. So what's the difference? Well, if you look at iron, you can see that it has different options for oxidation states. Iron may form a +2 ion, or it may form a +3 ion, depending on the situation. So those Roman numerals after the element here, it's telling you what kind of ion iron will form. The Roman numeral 2 means that this is the Fe2+ type, where this one down below is going to be Fe3+. And if you're 2+, that means you donated 2 electrons. Whereas Fe3+ will donate 3 electrons. So let's say we have an iron atom that wants to give away 2 electrons. Chlorine atoms, they can only accept 1. And so we're going to need 2 chlorine atoms to complete the puzzle in this case. That way everyone's got somewhere to go. But if iron is to donate 3 electrons, how many chlorines will we really need in this case? We will need 3. Each of them can accept 1 electron. And with this, the puzzle will be complete. Iron will give 1 electron to each chlorine. And we get a little bit different chemical formula for each of these. This one's going to be FeCl2, and this one will be FeCl3. The last thing I'll cover in this video is polyatomic ions. So sometimes certain atoms will act as a group when they bond, and some common groupings are shown here. They're called polyatomic ions. They're just ions that tend to stay together, and they tend to react as a unit in chemical reactions. These are some of the most common ones, but there are many others. Here we want to write the chemical formula that occurs when a calcium bonds with a carbonate ion. So the carbonate ion is this one. It is CO3 with a 2 negative. Now the CO3 is going to stay together, but the 2 negative tells us that this ion tends to accept 2 electrons. So it doesn't totally matter what's happening between the carbon and the oxygen right now. All that really matters is that that polyatomic ion wants to accept 2 electrons. With that in mind, we can draw calcium, and according to the periodic table, calcium's in the second column here, so it wants to donate 2 electrons. It'll form a 2+ ion then once it loses those 2 electrons. And then we have CO3, carbonate, which wants to gain 2 electrons. So it turns out to be a perfect match. All right, so Ca has 2 to give. CO3 is like a unit that has 2 spaces for electrons. If it could just get 2 electrons, it'll be happy. And luckily, calcium has 2 electrons to give. So they form a perfect pair, and you could cross the charges here, and you'd get Ca2 CO3 2, but we don't have to do that because we'd rather reduce it to simplest terms, just like you would a fraction. So we'll actually just write CaCO3, and that's it. This compound would be calcium carbonate, it's called. When you make a compound with a polyatomic ion, you just use the name of the polyatomic ion. You don't have to add like IDE or anything like that. This one says, write the chemical formula when a magnesium bonds with a carbonate ion. All right, so magnesium is in the second column. It's going to donate 2 electrons. And carbonate wants to accept 2 electrons. So similar to the previous example, we're going to have MgCO3. That would be magnesium carbonate. What about this one? Potassium sulfate. So sulfate is this polyatomic ion, SO4. So a sulfur bonded with 4 oxygens. It tends to accept 2 electrons, is what that says. We see that potassium K here is in the first column, so it actually wants to donate just one electron. So the sulfate wants 2 electrons. Potassium's only got 1 to give. So in order to fix this, we'll just bring in another potassium. And now the puzzle is complete. Potassium sulfate. And one last example. We want to write the chemical formula for iron 2 nitrate. Now the Roman numeral 2 means that this is the type of iron. Now the Roman numeral 2 means that this is an iron that's going to donate 2 electrons. If you look on the table, you see that nitrate only really wants to accept 1 electron. So we have that. Now, iron can give 1 of its electrons to the nitrate here, but it still has 1 more electron to give. So what we're going to do is bring in another nitrate. Now the puzzle can be complete, similar to what we had done in the past. But one thing that's new is how we're going to write this. It's a little more complicated than in the past, because before we just had 2 elements involved. Now you have an element with a polyatomic ion here. So let's write it like this. Fe will bond with NO3, but 2 of these are required. And so we won't actually just put a 2 at the end here and stop. What we're going to do is put a parentheses around the entire polyatomic ion. Then when we put the subscript on the outside of the parentheses, that subscript means that we have 2 of this whole thing. So we have 2 nitrates is what that means. So that'll be our answer for the formula for iron 2 nitrate.